Hi everyone, today I'm going to walk through the Module 2 notebook about ABC Bank's credit card approval project. I will go over the pre-processing steps, the future engineering techniques, and then compare how different models performed. The business problem itself is quite straightforward. ABC Bank wants to automate its credit card approval process instead of relying on manual decisions. We are giving historical application data and asked to build a binary classification model that predicts whether an application should be approved or denied. So let's start with the dataset. So here you can see it contains 9,709 records and 20 columns. The features include both demographic and financial information such as gender, car ownership, these things, and some of the several numerical variables like number of the children, annual income, age, these things. And the target value is a binary value. It's the one for approved and the zero for denied. So first we did the EDA analytics. Here, yeah. The first thing I checked was the missing value. Checked the missing value and duplicates. Interestingly, there were zero missing value and no duplicates rows. That made the pre-processing much simple. Because I didn't have a consider imputation strategies. So next, I reviewed the unique value counts and data types to clarify separate categorical and numerical variables. For example, gender has only two categories, while occupation types was 90. Understanding this helped determine the encoding strategy later. So next, we go to see these variables data type, and then we make so many plots like this to see the relationship between each of the variables. And then we focus on the skewness in the numerical variables. The non-children has a skewness of 3.6. Total income is around 2.66, and the years employed about 1.84. These are strongly right-skewed distribution, since the linear model like logistic regression can be sensitive to the skewed inputs. So I decided to apply box cause transformations. So um, after the transformation, you can see here, the skewness reduced significantly. Children dropped to around 0.89, and both total income and the years employed were brought very close to zero. This made the distributions much more symmetric and easier for the model to handle. And I also removed the ID column um, because it doesn't contain predictive information. It's just a client identity vendor. So for the categories, categorical variables, I apply the label encoding. This converts text categories into numeric form so models can process them. Although label encoding introduce an ordinal structure, tree-based model are generally robust to that. So finally, I use the auto visualization to generalize the automated visualizations. While it didn't dramatically change the decisions, it helped to confirm variables distributions and the relationships quickly. And then we need to talk about the feature engineering. So yeah, it's here. There were two additional techniques were explored: PCA and feature importance analytics. Before applying PCA, I standardized the features so that each variable has mean zero and a unit variance. This is very important because PCA is very sensitive to scale. The cumulative expanded variance plot shows how much information is retained as we add components. PCA can reduce the dimensionality and noise, but the trade-off uh, is interpretability. Once features are transformed into principal components, we lose the direct business meaning. For a banking application, that could be a drawback if model transparency is very important. And the second method is the random forest feature importance. While isn't feature engineering in the strictest sense, it helps identify which variables are actually driving predictions. This could guide the feature selection in the future iterations. And then we need to talk about the model training and the comparison experiments. So we split the data into 820 into the training and the test data sets. The first experiment compared encoding methods, binary encoding versus the label encoding on logistic regression and random forest. So you can see the results here. The results are surprisingly very similar. Logistic regression achieved 85 85 percent accuracy with the both encoding strategy. Random forest differed by only about 0.1%. So for this dataset, encoding choice did not meaningfully impact the importance. So you can see here the second experiment added is a k-means clustering feature. Um, the the idea was to create cluster labels and use them as an additional predictor. However, the result did not prove. Logistic regression stayed the same. The random forest accuracy dropped from 85% to 83%. So this suggests that the cluster labels may have introduced noise rather than useful structures. So one important issue appeared in the classification reports. Recall uh, for class one was nearly zero across all these models. That means models were predicting deny for almost everyone because the dataset is imbalanced. Highly accuracy was achieved simply by predicting the majority classes. This highlights why accuracy alone is misleading in imbalances classification problems. And then to explore about more advanced models, I use the H2O auto machine learning. Around 17 models were trained, including the GBM, XGBoost, Random Forest, GLM, and the deep learning models. And let's see the results. The top model by AUC was GBM5 with the 0.53 AUC and 88.5% accuracy. However, the most striking results came from the XGBoost grid search model. It achieved a 98.7% accuracy and 0.964 precision and 0.943 recall. This is a dramatically improvement compared to the early models. However, such a improvement suggests the possibility of the data leakage, maybe over or overfitting. further validation with the cross validation would be very necessary in this case, I think. Given that earlier models struggled with the class imbalance and had near zero recall, such a large jump raises questions about whether the models was exposed to information it shouldn't have had, or whether the test set was um, indirectly involved in training. And GLM performed poorly at around 52% accuracy, which is close to the random guessing. This suggests that the linear decision boundaries may not capture the complexity of the dataset. Deep learning may be also underperformed, possibly because the dataset is relatively very small for this. Um, and if validated properly, I think the XGB boost model would XG boost model would likely be the best candidate for deployment due to its balance of processing and recall. However, additional validation would be required before trusting it in real banking context. So let's go to the final part. It's about the reflection improvements. Overall, I think Box-Cox transformation effectively reduced the skewness, but encoding strategy and clustering did not significantly improve performance. This enforces that pre-processing decision are dataset specific and must be tested rather than assumed to work. Although SMOTE was imported in also in the notebook, but it was not um, actually implemented. Given the severe class imbalance, applying SMOTE or adjusting class weight would potentially maybe improve the core recall for the minority classes. Also using the cross validation instead of a single trend test split would also provide a more stable and reliable performance. Um, from a real-world perspective, I think deploying a critic approval model requires a careful attention to fairness and also regulation. Variables such as the gender age could introduce some bias, and the financial institutions are subject to strict compliance requirements. Model interpretability and fairness or auditing would therefore be essential before the actual deployment. So, yeah, I think that's all. Thank you for the watching. Thank you.